सर बोलते हैं कि वो ज्वाइन कर रहे हैं तो उनसे ज्वाइन हो नहीं रहा है, कोई दूसरी है, पता नहीं। मैंने बोला उनको 1150 वाली, लेट्स होप वो कर ले।
आप उनको मैसेज कर दीजिए फटाफट। हाँ ये हो गया सर, लाइव पे आ गया इसमें ऑप्शन, कमिंग सून आ गया इसमें।
Good morning, madam.
Good morning, sir. Very good morning, sir.
Good
So
morning,
shall we
morning,
start
sir.
now?
Good morning, Professor Lad. Welcome.
Yes, Dr. Dandekar.
Yeah.
Good morning. I can see you.
Good morning, morning.
Yeah.
Yeah.
Praveen sir, start. Ji.
Yes, I'm ready. Shall I start?
Neha ma'am is mute. No, hello, Neha will start. I will give you an opening remark of 1 minute and I will invite you. Before
Okay,
that,
sir.
Dr. Dakar
Shall
will
I
give
start
you
now?
your brief introduction. Yeah.
Good morning, everyone. I, Neha Patkar, take this privilege to start this webinar. We have 1,115 participants all over the India, including faculty, students, PhD research scholar, and industry people also. Now I request Dr. Andy Nadekar, Professor and Head of Industrial and Production Engineering Department for inaugural role. Thank you so much, sir, and over to you, sir.
Namaskar and welcome to everybody. On behalf of Department of Industrial and Production Engineering, Shri Govindram Saxeria Institute of Technology and Science, I, Dr. Milind Dandekar, welcome all of you with greetings and with wishes of staying safe at home during this lockdown period. It is a matter of great pleasure for us that in this today's webinar, we have Professor Bhupesh Lad, who is Associate Professor in Mechanical Engineering Department of Indian Institute of Technology, IIT, Indore. He will be delivering a webinar on smart manufacturing. And as you know, this topic is an upcoming area in the field of mechanical engineering in general, and we can say industrial and production engineering in particular. I hope, and not only hope, I am confident that today's webinar by Professor Lad will be useful and beneficial and informative also for all concerned students, faculty, research scholars, people from industry, and all other participants of today's program. Now I call Dr. Krishnakant Dhakad, who is assistant professor in our department, to give a brief introduction of Professor Bhupesh Lad, and then we will start his webinar. Thank you very much.
Dr. Krishnakant Dhakar, sir, can you hear me? Dhakar, sir?
Okay, Neha, you can directly call Professor Lad to start the webinar if Dr. Dhakad is not there.
Hello.
Dhakar, please introduce our guest.
Can you hear me?
Yes, sir, please start. You are mute now, presently. Dhakar, sir.
Thank you, sir. It is my pleasure to introduce our Dr. Bhupesh Lad. He is an associate professor in mechanical engineering department at Indian Institute of Technology, Indore. He received his PhD degree in the area of reliability in Department of Mechanical Engineering at IIT Delhi. Dr. Lad has 9 years of academic and research experience at IIT Indore and around 1.5 years of industrial experience in GE Research Bangalore. He has published research peer-reviewed international journals and conferences. He is author of the book Machine Stability, published by US. Was of national and international research project at IIT Indore. His research collaboration include IIT Mumbai, U Mahendra, Amit Bangalore, Hebitech Pithampur, and John Deere Pune. Dr. Bhupesh manufacturing laboratory at IIT. The laboratory has so far trained around 50 interns from manufacturing from across the country in the area of smart manufacturing. Dr. Lad has submitted 3 patents and he is actively working with to promote some of the work done by his research group. Received Hamid Cambridge Visiting Lecturer Fellowship of Cambridge in the year of 2006. In addition, the associated with the Interpret Development at IIT Indore and has been serving as Associate Dean Research and Development for the Institute since last 5 years. Dr. Bhupesh is one of the founder of startup company Tech Volume India Private Limited. Now I would request Dr. Bhupesh, please take the charge of this webinar.
Thank you, Dr. Dhakar, for the introduction and other members, including Professor Dandekar, for inviting me for this webinar. I hope I will be able to fulfill the requirement for this webinar. I'll now share my screen. Please let me know if you are able to see the screen. Can you see my screen?
Yes, sir, we can see.
Okay, good. So good morning. In the next 1.5 hours, I will talk about smart manufacturing or Industry 4.0. This title slide tells a lot about this subject. I see 3 things from the slide. One is machines are intelligent. You see here. The machines are intelligent because it is able to predict its health. Machines are able to communicate. There is some communication depicted here with other machines. Machines are able to make autonomous decisions. For example, this machine tells that I can take your load. So it must have taken some decision that I am free, I can take your load. So this is what we call smart manufacturing or Industry 4.0. But the question is how to reach to this level. So all right, let us try to find the answer of this question in today's presentation or talk. So this is how industries, especially the manufacturing industry, has evolved in the last 200 years or even more. From first industrial revolution that started in 1780 with the mechanization of the production, with the introduction of steam and water power. Then we saw second industrial revolution where the electrical energy dominated the industries and it helped them in mass production. Then came the third industrial revolution. It used electronics and information technology to automate the production. Today we are at the verge of, or in fact are talking about now the Industry 4.0 or fourth industrial revolution, digitalization, intelligence, and industrial Internet of Things are some of the technologies we can say or dimensions which dictates the fourth industrial revolution. In general, it helps the industry to induce intelligence in the factory. So you see, the all previous revolutions, it actually gave some we can say philosophies in manufacturing, like the mass production, automation in the production, mass customization. So what would be that in the case of fourth industrial revolution? So probably it will be manufacturing by mass. We'll see what is this manufacturing by mass in the next few slides. And to achieve that, we required a collaborative production system. So these are my thoughts that we talk about Industry 4.0. Everyone understands about the technologies that are behind the Industry 4.0. But how it is going to change the industries and what will industry achieve at the end of this Industry 4.0 is a collaborative production platform and manufacturing by mass. So let's discuss these things. So let's first have a different dimension about Industry 4.0. If you see from a volume versus variety curve, this is how typically all the previous three revolutions actually worked. Where from the high variety, we went to higher volume in mass production, and then again we started mass customization, but the volume came down. What will happen in the case of Industry 4.0 or fourth industrial revolution? My thought is this: if we have Industry 4.0, we are able to really apply it in our industry, or probably we can achieve this. This is a red curve which is added by me. It says that the high variety as well as high volume, though it looks conflicting, but it is possible. And for that, Industry 4.0 is needed. For that, a collaborative production system is needed, and it will lead to a new philosophy called manufacturing by mass. It is different from mass manufacturing. Let's say, what is this? I'll give you a small example of a collaborative manufacturing system or a production system. Let's say there is a customer. It may be a one customer or a very few customers. Let's say 5 customers, 10 customers, very few customers. They have a customized requirement of any product. To understand this example, let's take an example of book production, or let's say this is a printing facility. So the customer places an order for one of the book. It's very customized requirement of that particular customer or a small group of customers. Now you know how the printing industry works. If you print a book in, let's say, quantity like 10 or 20, its cost will be very high. But if you print it in, let's say, bulk like 500, 5,000, the cost will be even 1/4 or so. So let's say the initial cost with the initial demand D1 is let's say 5,000 rupees of that particular book. Now this is your industry, the production industry, or here I'm taking an example of publication industry, the industry that publishes this book, prints this book, and finally binds this and so on. So these are different machines required to do it. But the example is applicable to any other product. It may be a mobile production or anything. So the requirement comes to this industry. How this will come? There is an interface. So it may be through your all the e-commerce website, let's say Amazon, Flipkart, or directly customer will be able to interact with the particular factory. So the factory will know that, but for this particular books, I need, let's say, these 3 machines. So these 3 machines will form a group. These 3 machines now will interact with the customer. Now, for that particular thing, let's say it is a printing, this is binding, lamination, and so on. Now, they estimate the cost. While estimating the cost, they will have to do lots of industrial engineering calculations. For example, they will have to see their shop floor planning. If there are other books in the pipeline for the printing. They will see when the machine will be ready, what should be the best size, and what best size should I print it, and so on. What should be the inventory level? What is the raw material available to me, and what in what quantity should I order the raw material? And there are many other things. What should be the maintenance schedule? Suppose the machine is going for a maintenance, so it will have to look into all these aspects and reply to the customer, look, you want this book, I can give, this is your very customized requirement, I can give you this book. Here book means a product at so and so time and at so and so cost. Obviously the cost will be very high because it is a customized product. Let's say the cost is that 5,000 or something like this. Now how will it arrive to this 5,000 number? And let's say some time, like say 10 days, based on the internal planning, because it will have to look into its internal planning. But if you want a quick response, what you need is here is the internal planning should be done very quickly. So the if you rely on the conventional models, probably you will not be able to do that. You need a kind of distributed approach where individual machines are intelligent, they take their own decisions. So machine communicate with other machine and so on, and they make their own decision. Something what I showed you on my title slide. So this is required. Not only this, now these three machines will jointly will form a group, like we form a group in our Facebook of our BTech friends or our MTech friends, our industry colleagues and so on. They will form a group for this particular requirement, because this particular requirement can be made by this three machine. They'll say, if we produce it in this quantity, let's say D1, the cost is coming very high. Why don't we produce it in bulk if we can sell it? So probably this feel that the cost can be cut down to, let's say, 1/4 of this or even lesser than that. So what this machine will do, they will identify other customer who are interested. Let's say the book is of smart manufacturing. So there are various ways. One of the important ways is the intelligence of data. You know, when you buy a book, Amazon suggests you 10 more books. Correct? How it does? It's called the intelligence of data. Your purchasing history becomes a data, and that data becomes intelligent and suggests you few more books. So with similar concept, this industry or the group of industries will be able to identify based on the purchasing history or social networking activities, observing the social networking activities of the customer or the profile of that customer, that there are around 20 lakh more persons who are interested in smart manufacturing, at least for their research, teaching and so on. And they say, okay, let's ping them. So what I'm saying is the group of machine will ping to those 20 lakh persons or some number. Correct? So it is like one fine day you see on your mobile and you get a message from the Samsung factory or any other factory saying that, do you want this mobile? I can give you this mobile in 2,000 rupees. Its actual cost is, let's say, 8,000 or so. So similarly, this facility, this group of machine will ping to 1 lakh customer or 2 lakh customer who may be interested in such kind of product based on their purchasing behavior. And not all of them will reply. Obviously, few of them will reply. There are certain probabilities with which some few of the customer will reply. And out of those reply also, all the reply may not be positive. Some of the customer will say no, some of them will say I'll think over it and so on. But some of them will say yes, because suppose I'm an expert in smart manufacturing, I know that this is a good book and its cost is actually 5,000 and the factory is giving me or the publisher is giving me in 500 rupees. I'll probably quickly say yes. So there are different cases. Similarly, for any mobile phone, you know there is a mobile phone, its cost is 20,000 and the factory is contacting, the group of machines are contacting through the virtual agent, contacting to you and saying that if you order it now, you can directly get it in 2,000 or 3,000 rupees or 4,000 rupees. Actual value needs to be decided. So many of them will say yes. So suppose out of 2 lakh persons, even some percentage you say says yes, and let's say now demand from, initially the demand was of, let's say 1 book or 10 book, now the demand increases to 5,000 or let's say 10,000. So if they are able to attract 10,000 more customers, then the cost may go down from 5,000 rupees, it may be, let's say, 1,000 rupees because of mass production. Correct? So here you see, it was a customized product, but now the factory is able to make it in bulk. So it's called the manufacturing by mass. Manufacturing by mass, here mass means the customer. Manufacturing by customers. So customer is directly now interacting with the factory, and the factory is directly interacting with the customers or the probable customer, changing their customized demand into a generic demand for the mass production. And you know the benefit of the mass production then. But now how to reach to this 10,000? For that again, the factory will have to do its internal planning. What should be my batch size of this production, and what should be my sequencing of this? What should be my raw material order quantity? What should be the inventory level in my factory? What keeping the lead time in mind, and so on. It is also possible that this exceeds the current demand, current capacity of the factory. The factory may have to contact the neighboring industries so that they can outsource some part of the work. So again, there is an interaction between the industry and the neighboring industry, interaction between the supplier and your industry, interaction with the your factory and we can say the customer. So real-time communication and real-time decision makings are involved. With such kind of scenario or capability, our industry can produce a customized product in bulk and sell it, so we can achieve something called manufacturing by mass. And such kind of platform is called collaborative production system, where the industry is connected with customers, supplier, other system concerns, and so on. Or the kind of cloud manufacturing. Through the cloud manufacturing, they are connected with other manufacturing industries. So I hope at least you got an idea how the manufacturing by mass will be possible. And I think this is something which will happen in next 10-20 years, called the manufacturing by mass as a final or the ultimate philosophy of the industry 4.0. Okay, now coming to the research part of it, as I was introduced, that many of the a student also attending it, PhD student and MTech students. So for those students, developing such a collaborative production platform and associated decision models are of great interest to the industries and for the researchers. So you can think of designing your research problem around that. How to quickly do it. You understand the meaning. You have pinged a customer in the night, and if you say that, look, I'll get back to you after 2 days, probably he will not be interested anymore. But if you can finish this deal with the customer in, let's say, a few seconds, few minutes, the customer will be interested. Correct? So you need that kind of responsive system. Your current conventional ERP system or any other decision-making system may not be, MES system may not, or centralized system may not work well. So you need to design those kind of effective decision-making system. We will see how to do it. So these are some of the inputs for the researchers or the PhD or MTech student. So in specific, they can focus on 3 dimensions. It requires 3 things. One, intelligence of every industrial entity. Second is humanoid communication platform. And the fast, integrated and intelligent decision making. If you see the title slide, there also I highlighted these 3 things only. A smart machine is a kind of communication between the machines and fast decision making. Here I am additionally saying humanoid communication, because it's not the machine communicating with the machine. People talk about M to M. It's not only this. Machine should and may also be interested to communicate with the customer. That's what I just give an example. Okay, so these are the 3 areas where people can focus. Now coming to the technology side, these are some of the technologies. There are many more, but these are widely talked about technologies for Industry 4.0. Embedded system, cyber physical system, IoT, smart sensors, computer vision, cobots, cloud computing, edge computing, and many more. So there are 2 different views from industry side also and from academic or research side also. many of the industries, especially MNCs or OEMs, bigger industries, larger industries, they are also approaching the problem of Industry 4.0 from technology side. So many times when I interact with some of such industry, they say that AI is upcoming area. I want to do something. They don't know what, where, and what. They don't know. But say, let's do something with AI. This is one of the technology. So one of the approaches, you pick one of the technology and then see where it can be applied to solve any of the problem. On the other end, the other approach, which is normally adopted by SMEs, because they cannot afford this liberty, because in a bigger industry, larger industry, you have your separate research groups. They are continuously doing research on different technologies and its application in their field. But for SMEs, probably they don't have this liberty. So what they do is they go by problem. There is a problem and then they identify a technology. So we need to also look into both the dimensions. So even from the research side, many of the undergraduate students, very often come to me and say that I'm interested in AI ML, especially mechanical student, AI ML, AR VR, and so on. So they don't know too much about, they don't bother too much about the problem that industries can solve using this technology, but they want to learn something because they want to get themselves updated on this technology, because these technologies are in demand. But for a PhD student or a research student, it should be other way around. Like they need to first identify a problem from the factory or for any of the manufacturing industry, and then look into these technologies and which of these technologies can be used. Normally, a combination of those technologies are required, not only one of the technologies. So these are two different views: technology to problem or problem to technology. Both are important, and both are being practiced in industries as well as in academia. Okay, so there are challenges for Industry 4.0. First is, every solution provider has his version of smart manufacturing or Industry 4.0. There is a PLC manufacturer, there are sensor manufacturer, there are edge devices, there are software industries, and everyone has their own version, and they want to sell their own version to industries. But how to integrate this solution with the existing system is a challenge, and I think that is somewhere people are lagging. The solution providers are lagging. Integration of various technologies is a challenge, because Industry 4.0 is a highly interdisciplinary area. So integration of various technologies are important. A business-oriented framework to evaluate need and applicability of smart manufacturing or Industry 4.0 is needed. At the end, people, because return on investment is not very clear, so many times, so people are interested to understand what is the implication of any Industry 4.0 application in my business. So that kind of framework are needed. Handling the legacy assets, especially in SME, is a challenge. When I say legacy, many of the SMEs, even the bigger and larger industries, also they have their equipment, older equipment. They are there for last 20 years and even more. They cannot change them or upgrade them overnight. Correct. So on the other hand, when we talk about the smart manufacturing, which I just mentioned, we need intelligent machines. So how to handle those legacy machines? Even if you have one or two machines in a line, they are legacy, then you cannot have a complete, you cannot complete this network manufacturing or collaborative platform. So handling the legacy asset is very important in SMEs. How to convert this legacy asset into a smart asset or a smart machine is an important challenge. Integrating new solutions with existing ERP MIS system is very important. Otherwise, the first one, and every solution provider will provide you some solution, but how to integrate it with the existing system may not be answered. So the summary is almost all the industries are talking about it, but only few implementations are found so far in the real life practice. But again, there are also many other industries are going to that smart manufacturing scenario. We cannot say the complete conversion has happened. Another important aspect of Industry 4.0 is the business model. you cannot achieve the full benefit of smart manufacturing just by focusing on the technology. You need to accordingly change your business model. I'll just touch upon one of them because there are many other things I have to cover. So I'll discuss about first. Let's say servitization of product service system. Conventionally the manufacturing industry was focused on product selling. Now the scenario is changing.
Excuse me, sir.
Yes.
Sir, I request you to please maximize the screen. Participants are asking for maximizing.
It is already maximized.
The scroll. Okay.
It is already maximized. I am working with the full screen.
Okay. Then let me check, sir. Okay, sir. Let me check, sir. Thank you, sir. Sir, you can continue.
Yeah. So servitization of product service system. So conventionally manufacturing industries used to focus only on the product selling. Now the scenario is changing. They are focusing not only on the product but the associated service, because that is something which will give them more revenue throughout the life of the product. For example, you buy an RO system for your house. Earlier, they used to just sell the RO, and then whenever it fails, you used to call the service person and you pay for that. Now the RO manufacturer, let's say RO cost is 25,000 rupees. Now they sell the annual maintenance contract, which is around 5,000, 6,000, and so on. Correct? So in that annual maintenance contract, they earn profit from the annual maintenance contract also. So think from a manufacturing industry point of view, they are continuously earning profit from this. And for that, you need your service system ready. Similarly, for a gas turbine, it's not that you sell a gas turbine and one time you earn a profit. Now the industries are engaging into long-term contract with the users of the gas turbine. So they provide 10 years contract, availability contract, and so on. And if you want to do that, how will you do it? You need to also earn profit from this. So you need to install sensors, identify the right maintenance time so that you do the minimal maintenance and you achieve the required availability level. So again, all this industry 4.0 technologies will be required there. So the point is, if you put sensors and you don't use that sensor outcome in your business models, then probably you will not be able to justify the adoption of industry 4.0. So there are many other models like co-creation. There is you can go to the website of Lego, that robot or the toys manufacturing company, where the customer can design their own toy and then the company will identify the best one and will sell. So you can even earn profit. In the previous example where I was saying that the a customized requirement by a customer, think about a scenario, you design a very unique product, a unique mobile design architecture, something. The industry is ready to manufacture it, and then they say that as it is your design, I can share you the revenue. So think of, it's a completely different scenario where the customer is not only a paying entity, it can earn even the revenue by creating its own design and collaborating with the industries. So, such kind of co-creation will also be involved. If you have such a dynamic platform, you will have to use it and you will have to change your business models. So your innovation will come from your customer. When you say the innovation is coming from the customer, there is no limit of the innovation there. So industry 4.0 can even give birth to new dimension to the innovation using the co-creation concept. And there are many such other things like dynamic pricing, cloud manufacturing, mass customization, sustainability in manufacturing, etc. How to achieve? Now the question is how to achieve. I think again I am summarizing the entire thing into three parts. You should have a smart machine, product processes, and a smart communication system and a smart decision making system. So from the research point of view, you can focus on these three dimensions, and even for the implementation point of view, you need to look into these three. Let's talk about a smart product or a smart machine. I'll show you some examples. It's not that nothing is done in the Shri's, but there are few examples. There are many actually, but I'll pick couple of them. I'll show you some videos available on YouTube, and then we'll come back to it. Can you see the video?
Yes, sir, it's visible and audio is also clear, sir.
Okay. So, what did you see here? There are some smart robots. They are somewhere they must be communicating with each other. They're communicating with someone so that the requirement is known to them, and then go to the right place, pick the right shelf, and then take it to somewhere where the products can be easily removed. So this is how the Amazon is changing their warehousing using Kiva robots. There is another example from the manufacturing side. Just a minute. Yeah, so these videos are available on YouTube. You can watch in detail. But again, what did you see? If you want such kind of future factory, you need to work on various dimensions: advanced robotics, communication. There must be some decision making done behind it, so that the right component comes at the right place on the right time, correct, in right quantity. So all these required again those three things which I mentioned: smart machine, smart communication, smart decision making. And if you do this, what will you achieve? Again, the outcome are not very different. These are the things which any industry is aiming for last many years. These are the things: better quality, improved productivity, lower cost, on-time delivery. That this is what people tried using their lean philosophies, etc. Here also. But then the question is, if can you not achieve this without Industry 4.0? The answer is yes, you can. You can achieve these better quality, improved productivity, lowest cost, on-time delivery, etc. And people used to get it in their through their lean philosophies or lean concepts. But then why Industry 4.0 is needed? The challenge is that beyond certain limit, your conventional approaches will not deliver this. You can improve the quality, but up to certain extent. You can improve the productivity, efficiency, etc. certain extent. Beyond certain limit, you will require more data, fast decision making, etc. So that's where the Industry 4.0 comes into picture. The intelligence or the data-driven decision making, autonomous decision making, or better to say, these three things will come into picture, or Industry 4.0 will come into picture. So it is not like that you are not doing this, you cannot achieve this. You can, but after certain limit, you will find a saturation point. So you will have to probably automatically go into this direction of Industry 4.0. Okay. Let's say achieving smart manufacturing. Let's discuss about the first part, the smart machine. So these are some of the technologies, some of the areas through which you can achieve a smart machine. I'll give you one simple example of the hi-fi stuff. What you have seen just now are there. But when you actually start doing it, you go to your factory and you will find many legacy machines and so on. How to do it? So I will start with a similar example. The first one is smart machine or smart product using a kind of legacy machine. So you see, this is a real example that we have done in one of the manufacturing industry in Pithampur. This is a fencing and centering machine, a legacy machine, as no, many of the industries have such kind of machines. So what we did is we tried to convert this into a smart machine. So we designed its digital twin. So converting, so the first step is always to convert the physical machine into its digital twin or get its digital ready. When you say digital twin, it is the digital counterpart of the machine which is aware about the machine, about its past, its current status, and can predict the future. That's the typical characteristics of any digital twin. So I want a digital element or counterpart of this machine which can tell me about it, the past of this machine, which can tell me what is the current status of the machine, which can tell me about which can predict the future of this machine in terms of when it will fail and so on. The challenge was that's a legacy machine, how to do it. So we came up with a event-based algorithm where we identified all possible events of this machine, event, end event, and the final final end event of this machine. And we linked one of the data source with it. And if some of the data, for some of the data source, for some of the data we linked it with the controller. So the controller had some of the data, we could extract some of the data. Then some of the data, there were some few sensors, not many sensors, but there were many things which were not being captured. So what we did is we designed a manual interface, a kind of human machine interface, a mobile tab or a mobile or a tab kind of system where all these events and the sub events and the end events are programmed. So ultimately, if any change happens in any of the end event, will be a trigger which manually you can press it, or if there is a sensor, automatically it will be pressed with the sensor outcome or the controller outcome. So it is a flexible system which can be replaced with a completely automated system in future, and it can be customized with any such machine. That's how we did. So now, for example, let's say the machine is down. There is an event, and the sub event is the machine is down because the operator is not there. So now the question is why the operator is not there. The operator has gone on bio break, or absent, operator is absent, and so on. So someone needs to just press one button for the end event, and then it gets recorded in a standard format in that machine. Similarly, machine has failed. So people, as soon as the machine fails, the operator will press one button, that machine has failed. The information will go to the similar digital twin of the maintenance department, and that they will get the signal. The person will come, they will analyze, and they will find that the particular bearing has failed. So that they will, in the same tab, they will. Then there is a, so this cyber twin will have a structure. So this is the structure how we yes, any query? Has various parts. One is a database. If the data are large, then we have the big data techniques, and most important one is the analytic engine. So in this analytic engine, there are various models. You can let's say you want to simulate this machine for next 1 week and identify what would be the availability of this machine in the next 1 week, etc. So you can simulate that using the data that we have stored using the event-based algorithm, and then you need to just plug a simulation model. So you can design a simulation model for failure simulation and repair simulation and plug into this analytic engine. You want to predict the life of this machine, you need to plug life. So I will talk to the networking profile, Facebook profile of this machine, and ping it, ask what is your remaining life, send it to a digital twin, and digital twin will run this prognostics model, get the data. For this it will get the data, which the data is coming from this event-based algorithm, and return the result as RUL. My remaining life is, let's say, 20 days. That's it. Correct. So that's how the machine becomes intelligent. Even a legacy machine can be converted with certain adjustment into a smart machine, so that the rest of the things, the smart decision making and smart communication, can be taken care. Example which we did in our laboratory was on a CNC machine. The machine was slightly more advanced. So we put some sensors and we monitor the health of this cutting tool. We put some accelerometer here, and then all this data acquisition system. And we predicted the remaining life of the cutter when it is actually working, because when the cutter is working, slowly it will wear out, so the life gets reduced. So we were able to predict the remaining life using the vibration reading of that cutter. Not only this, we could link this cutter remaining life or the wear value with the quality control policy of that machine. So let's say earlier there was some, like the sample size was 10 and they were taking a sample every 1 hour. Now as the cutter gets worn out, or the life gets reduced, now it is more, the wear value is more, so you need a more stringent quality control plan. The conventionally industries go with a static control policy. The control, there's a sample size, and even the sampling frequency remains constant. Here, with the life of the cutter or any other component for that matter of the machine tool, the quality control policy gets updated. So it's a dynamic quality control policy. See the benefit. So conventionally we were able to find any out of control on the 6th sample or the production run. Now with this dynamic policy, we were able to do it at the 4th production run. So initially, conventionally it was producing 60 faulty product if there is any problem in the machine. Now here only 6 faulty products are produced, and the out of control of the machine is identified. Correct. These models of the prognostics, model of the machine performance, quality control model, everything were stored in the digital twin, and the machine can take the real-time decision. So this was done under a different project. But this is also important aspect of a smart machine. So for the researchers, again, I'm coming to the PhD students, MTech student. If you want integration of the prognostics with shop floor decision making is one of the important areas for research. It has huge scope. You can take similar kind of projects for your research. Yes. Then another part is asset administration shell. You know what happens is quite often, we consider this mechanism between the mechanism to facilitate the interaction and information action between the physical asset and the digital asset and the human as granted. We take it as a granted, means the data coming from a physical asset will smoothly flow to its digital counterpart, and it can easily communicate with the human. But that mechanism is not that easy. Correct? If I ask what is the diameter of the bearing used in, let's say, any of the machine, with the machine, so a human is asking, the machine should understand my language. Their language is different. You are talking to a Japanese in Hindi, he will not understand. That's the same concept. So how to bridge that? The answer is asset administration shell. So it considers all the standard ways to store the data, collect the data throughout the life of the asset. When the product is actually designed, in fact, from the concept stage to design stage to production stage, and usage, upgradation, maintenance, and end of life stage, all the things are stored in a very we can say a standard manner. So the corresponding technology is called the asset administration shell. So this is the physical machine, this is the shell, and there is all the digital twin is outside. So this digital twin or any other entity interacts with this shell. So this is the shell which ensures that standardization, so that we understand, or anyone will understand the queries asked by the human or any other machine. So various dimensions of asset administration shell development are not yet explored. Only few Japanese universities or industries have done something in this area. So this is a very important area of research, again, for the PhD students. So I haven't seen any such implementation in industries in India as of now. Okay, so now we have discussed this part. At least few with some examples. There is no end to this. There are many other things how to make a machine smart. We will again take one example at the end, real life case study. But there's a second part. Let's come to the second part, called the smart communication. So again, you need a humanoid communication system where human and machine to machine communication and the machine to human communication can be done smoothly. And you need to also think about the connectedness in smart factory. What kind of connections are possible, and what are the challenges and issues under those connections needs to be addressed. So this is how a system or the communication system will look like. You have a machine, you have an administration shell. There is a digital twin. It will extract the data through its in a very standard format from its asset administration shell. Similarly, there is another machine, the physical machine. Sorry, there's some problem. Okay, and this is the administration shell of this machine. There's a digital twin. This machine every machine will have its so-called Facebook kind of profile through which anyone can interact. Let's say this is in my lab only. One of my student wants to talk to this machine. It has all the digital twin. So he's wearing a VR glass, and once using the VR glass, it scans to this code, and it asks what is the current temperature or remaining life or the condition of the machine. So this information, when he asks, it actually asks to this, and it goes to this, and this finally gets the data from it and reverts the answer, and the answer is displayed here. So human, here you can say a human is interacting with a machine, whatever it is asking. You can even virtually stop. I can stop my machine sitting my home. I can give command to the machine sitting in my home. So something like this is possible using this kind of humanoid communication platform. Developing such platform is very challenging and important aspect. Many of the computer science students are working in this area, and can be taken up as a good project. There's another example, machine-to-machine communication. I showed an example, machine to communicating with the human, or human communicating with the machine. Here, this is an example where machine communicates with other machine. So you see, these three machines are required to produce one of the part. They make a group, and then the machine one is talking to other machine, saying that I have dispatched this product, you will receive it at this time. The machine three will say, I have broken down, can you take my load, or I need maintenance, and so on. The maintenance department will say, after this many hours, I will be able to come and repair you. All this kind of communication should happen. So such kind of communication platform are required. Many persons are developing different kind of such platform. We have developed something like this. The product is called Industry Smartware. Second part is the connectedness. You see, in industry, various forms of connectedness are possible. Like you connect the sensor with a PLC, or you connect the sensor with a DAC and connect it with the PLC or the edge devices, or directly with the cloud, or connect the PLC with the edge devices, or connect the PLC with, normally we don't connect PLC with the cloud because of security reasons. You connect the PLC with SCADA, connect the sensor with PLC with SCADA, and PLC with edge devices, send some of the data from the edge devices to cloud, and so on. So there are different options. The benefit of edge devices that you can perform the local level analytics right at the machine stage, right at the sensor stage. Now the sensor comes with some processing power, so you can do some analytics there itself. So the various levels of connectedness in manufacturing are there. You need to identify what is the best level. When you say identify, there are these issues: responsiveness, cost involved into it, security. These are the aspects that you need to consider. If you are sending all the data to cloud, the response may not be very good. But if you want higher responsiveness, you may probably use the edge devices. But it has also its drawback. You cannot do too much of the processing, but the safety or security will be higher. Here, not here. So you will have to see which connectedness model to select for your particular case in your particular industry or particular machine. Industries need to decide appropriate level of connectedness, and researcher can evaluate the cyber risk of various level of connectedness and develop mitigation solutions. I mean, let's say suppose there is a computer science student in this present in this talk today. So what they can do as a research problem, they can see if there is a communication network developed, and if I connect my sensor to PLC or sensor to, let's say, the cloud, or sensor to edge device in three different cases, and if I induce some of the possible cyber threats, you induce it in your system, see how it behaves, which one is better, and how to make the system more threat proof. So you will have to write those kind of algorithm, like a kind of antivirus kind of system for this kind of thing, how to protect your system in all these three cases. And then you can present to the industry that, look, if you are sending the data to the cloud, this algorithm will protect you, and so on. Correct? So encryption and all this, you need to work on it. So these are some important research areas. Okay, so now we have discussed this first two part in brief, how to actually get a smart machine and a smart communication network. The next one is smart decision making. The conventional decision making may not work well. I'll just, many of my industry colleagues sitting here, the friends will appreciate this. How many of you really use a scheduling algorithm to schedule your jobs? Probably the answer is very less number of the industry. Most of them rely on their experience. Why? One thing is such algorithms are very costly, or the tools are costly. Second thing is it takes lots of time, computational time, and industries want quicker decision. So if your algorithm is not able to take quicker decision, it is as bad as taking a decision through your experience. So they go with the experience decision. I have examples where this many of the industries who were taking the experience based decision. I showed them that your experience based decision is not very effective and you are losing lots of revenue. So please evaluate your experience based decision, first thing. But the quickness of the responsiveness of algorithm is very important. Now think of a situation which I mentioned in the very beginning. The machine contacting to the customer through its Facebook profile or the WhatsApp or whatever way, you cannot hold on the customer for a longer time or for such chat. You need a quick decision. In seconds, you need a decision. For such decision, whether your current decision making system is ready, answer is no. A simple scheduling problem takes many hours to solve. Realistic problem. So we need a distributed decision making. Probably this is my area, but there may be few other things. We need an integrated decision making. Why integrated? Again the same example of that printing of a book or production of a book. There was an integration of the manufacturing industry with the customer, integration with the supplier, integration with the other neighboring industries or outsourcing industries, and so on. So the decision making needs to be integrated. Correct. So an integrated decision making is involved. Once you integrate the decision, your decision elements are increasing. So the decision making becomes very complex. That it will again further complicate the computation, increase the computational time. So how to solve this? A distributed decision making is required. Distributed in the sense, as now with this you have a smart machine. When I said smart machine, it can take decisions. So why not utilize that? Why you need all the data to go a central server, use your conventional MIS ERP system? I'm talking about the conventional. There are some modern systems or comes which way you probably might be utilizing the distributed intelligence. But the conventional system used to process all of them, run a single scheduling algorithm or simulation model and come up with some and then associated optimization model, and used to come with an optimal schedule. Why you need this centralized computation? As your machines are intelligent, why not to go for a distributor? Why not to allow the machine to take your decision? In your family you have different members that has or have their own intelligence. They take their own decision. And then there is a communication also among your family members, and sometimes when your kids take decision, you may probably take a second layer of decision, say no, not like this, you do like this, but they take some decision. So that's how we work. So typically in a smart manufacturing system, the machine should work like a human, should utilize their own intelligence, take their own decision, communicate with the relevant entities, and update their decisions as and when required. So local level decision and the global level decision making. So these are the two important aspects. I'll show you one example which we have done. See, let's say there are these 4 machines, and this is an example of maintenance optimization. I want to optimize the maintenance schedule. I'm just considering that each machine is made up of 3 components, and I want to identify the optimal maintenance or replacement schedule of these 3 components. And the machine is producing, let's say, 4 jobs. So I have 4 opportunities. The maintenance can be done before the start of each of this job or batch of the jobs. So one means before the start of the first batch, yes. Before the start of second batch, no. Third batch, yes. Fourth batch, yes. Again, this is for one component, second component of the machine, and third component. So now you see, if I have 10 machines, 6 each having a 6 component and 7 opportunities, means producing 7 batch of different batches of product, my problem size will be like this, which is again a very small example. But if you take a realistic example, this will be of the problem size will increase exponentially. With this, the problem size is that complex. If you run even a simple genetic algorithm or your any other optimization algorithm or meta heuristic will not be able to solve, or even if it solves, it will take time, or suboptimal solution may be obtained. How to solve this problem? So now you know enterprise is actually the machine. Machine is not of my interest. I have a connection between machine and my this digital twin. So now I'm mostly interested into this. Machine is just producing parts, but whatever is happening, everything the digital twin is aware, and it knows its past, it knows its current status, it knows it can predict its future. So this digital twin can take a decision on behalf of the machine. So they can take their local decision, they can communicate with themselves, they can communicate with the maintenance department, and can take a global decision. So this is how we did it. This is a distributed decision making where individual machines runs their own decision making algorithm, takes a decision, communicates to let's say maintenance department combines this decision, their preferences, comes up with a better decision, final decision which is actually implemented. Correct? Now see the benefit of this. You see the centralized conventional approach for a problem size of 2⁻30. This is the runtime using a genetic algorithm or memetic algorithm. This is the most accurate approach, brute force. This is the objective function, the minimization problem. This is the best solution, but this is the time, 36,000 seconds. So obviously this is not a practical solution. And beyond this, brute force is not, or complete enumeration is not possible at all. So we give up here. The only solution is use the genetic algorithm, memetic algorithm, or any other meta heuristics, but the time will be of this order, 1300 and so. Obviously we will get a solution which will not be as good as this, but somewhere closer to it. Now what if we go for the distributed approach which I just mentioned in the previous slide? This is what we achieved, 0.6 second compared to 1357 seconds, which is a huge benefit. Now again come to that first example of the book manufacturing, or the machine contacting with to the customer, and the machine is able to make its decision, any of the decision, in such a small time, 0.6 second versus this. It can quickly take decision and tell to the customer, look, I will be able to give you this at this cost at this time. So you will actually see the objective function value. Again, it is not as good as this, but better than this. Correct? Even if it is not better than this, you don't need to worry too much, because now the next generation business model will be dictated with this time. Because if you are able to quickly answer to the customer, probably you will capture more market share. So whatever suboptimal decision, even if you take here, is okay, because you will compensate it using the more market share. So this is how it worked. So better solution in a significantly lesser time. This is the time of our approach, distributed approach, the conventional approach, the time required, and you see the objective function value. We are more or less closer or even better for many of the cases. Now the another dimension is, what if the problem size, instead of 2⁻30, now if I increase it to this, let's say 2⁵60, the time required was this. Now 2⁻1512. When I said 2⁻, means this many combinations needs to be evaluated. This is the problem size. The time required is now 297 seconds. Just 50 seconds extra, around 50 seconds extra. See the scalability of the problem. So here there are 6 machines. Now we have 27 machines. So even if you increase the number of machine, number of component in the machine, number of jobs to be produced on the machine, the problem size will increase, but the algorithm is scalable. The algorithm time will not significantly increase. So similar approach can be developed with job scheduling. When a machine talks to each other and makes their own schedule. Previous one was an example for maintenance schedule. This is job schedule. Can be done. This line shows that they are talking to each other and comes up with some solution. And with this kind of solution, when we compared with the available algorithm, we found that we can significantly, this is a saving in terms of the make span, the time required to produce some of the parts using the distributed algorithm. Now, the benefit of this, another benefit of this. See, this is a small example where there was initially 6 product, 1, 2, 3, 4, 5, 6 product. I obtained the sequence, the optimal sequence using any of the algorithm, and the make span is, let's say, 87, which should be minimized as much as possible. Now, what happens is, when I am producing, let's say, second product, a new demand comes. So if we go with the conventional way, many of the time industries, what they do is they put the new demand at the end. If you do this, the make span is 116. But as my algorithm is very fast and I'm here, why not to reschedule it? And then I found the new sequence like this, and the new job comes somewhere in between. The make span is this. Correct. So this is the benefit, the quickness of the algorithm. So you can get this if I able to quickly reschedule. So dynamic planning is possible. You are talking to a customer tomorrow, some more customer says, yes, I also want this. So you can quickly replan your entire schedule, maintenance plan, quality control plan, inventory level, inventory or the ordering plan, and so on. If you can do this very quickly, you become very responsive, you get benefit on this, and so on. So a responsive operations planning system is must for a collaborative manufacturing platform. Developing such an algorithm are challenging. Industry engineering students have the opportunity here to develop such algorithm for the use of AI. In any of these algorithms, I haven't used any AI, where the algorithm learns itself and comes up with the solution. So artificial intelligence can be used in such kind of distributed algorithm, and this will make the approach more closer to the industry 4.0 requirement. This is the example where we not only the distributed, but we integrated the operations planning. We integrated the inventory planning with the scheduling, production scheduling, quality control plan, and maintenance plan. We integrated all of them. Because again, in my very first example of that machine contacting the customer for the changing the demand, attracting more demand, and contacting with the supplier, neighboring industry, planning within the industry, you need a integrated planning. So we found using an integrated plan. So we are integrating from the decision perspective. But when you say computation point of view, we are still distributed. So it is integrated, yes, distributed. This is one of the, we can say, this both the words are conflicting, but we are able to achieve, and we could show that this will be very important for next generation manufacturing industries. This is one of the very important results that we have achieved, and you can see our algorithm, the time lapse. The blue line shows the time lapse, and the integrated planning we could achieve here. And the integrated planning at different level we can integrate. So our time was very less, and our objective function value was also closer to the centralized approach or even the non-integrated approach. So these kind of approaches are required. Literature are there. You can refer to such kind of approaches and come up with many such approaches. Mostly the extending such approaches to entire value chain. Currently, this is done only for one of the factory. But now, can you extend it to with the supplier, with the customer, with the neighboring or the outsourcing industry and their shop floor? Because for many of the OEMs, the SMEs are the supplier. So the OEMs require real-time interaction with their with the SME or the component suppliers, so that they can, in that Airbus example, the component was directly coming to the line on right time. So there must be a coordination with the supplier also. So such kind of algorithms needs to be developed. But the distributed will probably give you the hint how to develop this. Okay, I hope I have some more time, around half an hour more.
Yes, sir, but it will be better if you summarize in few minutes.
Okay, what I'll do is I'll just quickly take you to the case study, because there are some industry participants are also available.
Yes, sir.
So I'll take you I'll try to summarize in 15 minutes. So the first part was mostly on the research side and some of the implementation also. But then, yeah, so how to align Industry 4.0 transformation with the business goal. So I'll take you to a very small case study, which we have done in collaboration with IIT Bombay. We are IIT Indore is leading an industry academia consortium on smart manufacturing, where all such projects are listed, and these are the partners. Royal Academy of Engineering, Cambridge. Royal Academy of Engineering is the funding agency. University of Cambridge is the partner. Mahindra and various other industry partners are involved into it. So under this project, IIT Indore and IIT Bombay developed a case study where we actually selected an industry because they were really motivated to move on to their digitization journey. The case study is of MP Engineering and Machine Tool. Very small industry, is a small industry, but really motivated industry to move further on their digitization. So I'll probably skip the overview of the industry, but I'll highlight only few points. They were mostly focused on improving their quality. Their main goal was to increase the customer rating, and then they these are their suppliers, customers, all this, their basic company details. This is how the raw material flows from from the raw material section to different process machining section, and finally packing, inspection and packing. Okay, so when the raw material comes, it comes with certain heat number which shows its chemical composition. The industry maintains some raw material sheet which provides the basic detail of the component, but there are no proper linking between these two. Then when the component goes to different machine station, the operator fills this and keeps it with himself or herself, because their main objective was to monitor the work done by the operator, and so on. Similarly, there was an inspection section. At the end, it goes to inspection. Inspection sheet is also created, but the inspection sheet was not linked with the production sheet, and production sheet was not well linked with the heat number or the sheet given by the supplier of the raw material, and so on. This again, we also analyzed their shop floor. Many of the planning were experience based. These are the two things we identified on their current shop floor. Then I'll quickly escape because of the lack of time, but we found that even for such a small industry, decision making are very important. Many of the commercially available decision making tools are normally not used in the industry. We need an online decision making tool, and so on. But most importantly, then we started digitization assessment. So this is an important aspect for any industry. They need to first assess their digitization requirement. So we did this for this particular industry. So their goal was this. We captured their goal. There are many goals, but we asked them to prioritize or give the best or most important goal. They said that we need the higher ranking of the customer from the customer. So it had three different sub goals, and each of this had so various functions were involved into it. For each of this function, there are subcategories and the associated items which we listed after a discussion with the industry. And for each of this associated items, we prepared a questionnaire where we asked them to rate, like, for example, do you monitor the machine's health in real time? If yes, then A. If B, no, then partially, then B. If you are just starting this, then beginner. If no, then D. So if D is there, score is 0. If A is there, score is 4. So we prepared questionnaire for all the these associated, many such questions for each of the associated items, and then we finally identified the score of all the associated item for the function, and then we transferred it to function, subcategory, and finally to the function. With this, we found that this particular industry, this is the important graph. This is their current level on the digitization. Current level. So for different function, quality function, they are here, and their target level is here. Similarly, for production, they are currently here, their target level is here. So we found that the current level of Industry 4.0 is 1.25, which is a beginner level, and the target level is 5.16, which is an expert level. So even for each of the functions, we identified what is their for the subcategories, what are the different target level in the current status. And then we identified for one of the which was the most important was the rating. We identified they want to improve the rating. So based on the questionnaire, we proposed this solution. So we found that they are yes, but they want to continue to be in the green zone, means they want to be in that rating zone only. For that, one of the solution that we identified was the traceability. I'm quickly taking you to this because of the lack of time, but the traceability is the solution which was identified, and we proposed for this industry because SMEs, you propose them a very high-fi solution with, let's say, lakhs of crores of the rupees, it may not be implemented. But this is a solution which we even implemented. Two stages of these are already implemented. First, we propose a barcode-based, paper-based system where all these different data collection were synchronized in one file, and the barcode gave all the information. And we designed a bin for them. So the bin was associated with all the raw materials, and it was moving with this barcode, and at the end the final packaging. So anything happens with the final product, the customer can just scan and get detail when it was shipped, what was the processing, what was the quality inspection. Even the manufacturing industry can know this. If any problem comes with that particular component, it can track the entire history of that particular component. So this is the first stage solution. When we implemented the first stage solution, what happened? I'm just giving one example. Their answer to this question: do you extend the to what extent can product be tracked throughout the life cycle? Earlier their response was B. Now it has changed to C. We again re-evaluated it. So the total score before was 1.37 on the customer side. Now it has increased to 1.48 just by in doing this small project on digitization. Then on the first stage, then we said, okay, the second stage we develop a mobile tab or a tab based system where the person can scan the barcode through its mobile, and all the entries will be automatically will be entered in that mobile only. So with this, again the score changed from 1.48 to 1.71. And the third, and we implemented up to these two stages. So now that they're moving on their digitization journey. So again, when I showed you two example on YouTube, that's probably extreme example. But when you take your own industry case, you will have to move with this stage by stage solution, and you should have a long-term plan to move somewhere on your digitization journey. So this technology roadmap was provided to them, and we implemented two-stage solution. The third stage was a blockchain-enabled solution, so that only the required data goes to the third party, and so on. The security was enabled, and so on. Then with this, we expect that from 1.71 they will go to 1.84 on their digitization score, or the industry 4.0 readiness score. And then the next stage that we haven't yet thought of, but will be using the HMIs, smart HMIs, where the inspection will be done and the data will be recorded through this such kind of smart HMIs. So these are different stages of solution, and they are going stage by stage. They are implementing it, and with that, their digitization level, industry 4.0 readiness level is increasing. So now the industry was a very small industry, but they are interested in digitization. Why? Because their customer, which is a larger industry, is interested. And now in future, probably the OEMs will dictate the digitization requirement from their supplier or the SMEs. So this can be for the SMEs, digitization readiness will be one of the selection criteria by many of the larger industries for the supplier. So the summary is the better customer ranking they could achieve. In the current solution, product traceability will also help in better data analytics. For example, which machine is mostly creating problem, process capability of different machines, etc. can be these are the additional advantage which can be achieved. More analytical decision making is possible. For example, accurate delivery commitment, production planning, etc. So the data that they have captured, we haven't used it for such decision making, but these are the next level. If they do this, they can further improve on their digitization score. Multi-stage technology roadmap may be useful for SME. That's what we identified, and it is working well. Industries may decide where to stop on digitization depending on the budget, available budget, time, etc., they can say, okay, now I don't want a blockchain based solution, mobile based solution is sufficient for me on this, let's move on to the next objective, and so on. So overall summary is, we need to think beyond the buzzword like Industry 4.0, IIoT, smart manufacturing, and related technology solutions like machine learning, cloud analytics, blockchain, etc. Smart manufacturing or Industry 4.0 is important even for SMEs. Digitization projects should be clearly linked with their business goals. That's how we did it in one of the case study. A technology roadmap is important. Roadmap is important. You cannot say just you work on AI, ML, and then you will improve. You need a stage-wise solutions and the corresponding benefits so that the return on investment is also very clear to the industries. Digitization may not always require very high investment. This is what we know. The many of the SMEs feel that it requires lots of investment, but we showed that if you go with stage-wise investment, even a paper-based solution help them in improving on their digitization level, and it did not require any investment for that matter. Very less investment, nothing. Mobile-based solution required probably some investment, and so on. Digitization may help in identifying typical analytic opportunity, which will ultimately result in better system performance and lean manufacturing. So to summarize everything, all it takes to get into smart manufacturing is probably a smart thinking and a commitment that yes, I want to go for Industry 4.0, because today or tomorrow this is going to be very important, and I should start it from now only, and I should start identifying the right area, right technology, and proper stage-wise solutions for my industry. That's it from my side. Thank you.
Thank you so much, sir. Sir, can we now take few questions from the participants?
Yes, please. I am available for the questions.
Yeah. Thank you, sir. Sumit sir, over to you. Anil sir, question please.
Yeah. Hello, sir. This is Anil Sharma. There are around 18 to 19 questions asked from the participants. My first question is from Aparna Deshpande. She wants to ask that what technology we use for data collection.
What technology we use for data collection? See,
yes, sir.
If I understand her question clearly, data collection, there are various things. You can use either the sensors, you can collect the data from the PLCs, you can use the HMIs or the manual tab kind of system. But the challenge is, let's say, how to extract the data from controller. Many times they are not open. So there are technologies called, let's say, empty connect. So such kind of empty connect kind of technologies can be used to extract the data in a standard format from controller. Similarly, from sensor, you need to write your own code using the LabVIEW, etc. You can extract the data. But the challenge is this data should be stored in a standard format. So the asset administration shell part, which I mentioned, is very important. So you need this kind of technologies. The hardware technologies are there. Then there are software things like the empty connect or the LabVIEW, etc. But then you need to ultimately link everything with that asset administration shell concept. So I think these three things will be very important when you collect the data.
Okay, I think it's clear now. My second question is from Anmol Jadhav. What is the difference between Industry 4.0 and IoT?
I'll say Industry 4.0 is more about IIoT, Industrial Internet of Things. Internet of Things can be anything. You link two dustbins and the जो गाड़ी आती है कचरा कलेक्ट करने वाली उसको लिंक कर दो. That is IoT. That is there is Internet of Things is there. But when I talk about Internet of Things for industry is such kind of scenario which I was talking about. That comes under mostly under industrial Internet of Things, and people try to differentiate it, but for me, it is same mostly. But IoT or IIoT talks about the communication part. When I say Industry 4.0 or smart manufacturing, it is a bigger thing. It requires IIoT plus other thing like decision making algorithm or the corresponding automation, robotics, and all this also. So IIoT is one of the elements in smart manufacturing.
So my another question is from Nitin Chobe. That is, what is the difference between smart decision making and artificial intelligence?
Smart decision making may use artificial intelligence. That's one of the way to do it. See, when I say artificial intelligence, so let's say I'm optimizing something, correct? So when I say distributed decision making, so I was taking some decision at individual machine level. There is no artificial intelligence. Every machine has its own, let's say, maintenance optimization or production schedule optimization algorithm. So it is optimization, but it is smart because individual machine is taking its decision, and these decisions are being communicated of preference of decision, not only one top decision, but 10 decision, let's say, from each of the machine goes to, let's say, the central agency or the central agent or scheduling agent, and the scheduling agent or the maintenance agent then combines that and runs a second level algorithm called the greedy algorithm, and comes up with the global optimal, and that which is finally implemented. This is a smart way because individually I am taking the decision. But now if I want to include so-called machine learning here, machine learning in it, I can decide how many solutions to pass on to, let's say, the central agency. I want to decide that. For that, I can apply the machine learning. So based on the type of the problem, type of the demand, type of the machine, age of the machine, and cost of the products, everything, all these different parameters, machine learning algorithm will automatically suggest to individual machine that, look, in such scenario, you should pass only three top solutions to the maintenance level. Agent or the second level agent. So this becomes a smart decision, or again it is a smart decision only, but here you are including machine learning also. So machine learning can further help you in making the smart decision. So that's how it works.
I think it's clear to him. My another question is from Simriddhi Gupta. She want to ask that how much does it cost to implement an Industry 4.0 solution?
If you talk about that Airbus example or even the Amazon example, I don't answer to this. I think you see the example which I showed in the last, a very small industry. You see even in the shop floor, you will understand it's not that hi-fi industry. And when I say Industry 4.0 implementation, there is no end to it. Even that Airbus example, I can tell you 10 more things they can do it which are not done at the moment there. So there is no end to Industry 4.0 solution. So we cannot say that this is the cost of Industry 4.0 solution. And if you apply, invest this much, your industry will be 100% Industry 4.0 ready. It's a stage. It's a journey from your current stage to a complete Industry 4.0. And the complete level also depends on you, how much you want. One industry may want different level, other industry may want different level. So it is not about the Industry 4.0, but yes, you can say one of the Industry 4.0 solution, the cost varies. And as I showed in one of the example, even a paper-based with the paper-based solution with certain barcoding, you can start your Industry 4.0 journey, and that probably costs them nothing except the cost that you might have charged to do this consultancy for them, very minor minimum cost. But they are able to do something on in the line of Industry 4.0. Second stage also, as every operator had the smartphone, they did not have to spend anything. Just scanning that using the, so we developed a mobile app. There's that very small cost and hosting it on some of the servers. That's it. Nothing more than that. So, but when you go for the more stage like blockchain, then you require different IoT, different IT infrastructure, smart gauges. You require more cost. So there is no final, single answer that this is the cost. It depends on the problem. It depends on the level you want to go, and in that level also how you want to go. Step by step solution will actually can be proposed, and the cost but it doesn't always require very high cost. Even for a very low cost, you can slowly move on to journey, and ultimately once you move on to that journey, you will see the benefit of it. You will get the revenue out of it also. So it's not actually cost. It will result into some revenue. So this is how it goes.
Sir, now it's come to the last question. Amit Prajapati want to ask, in smart communication, there is a risk of cyber attack. So how can we improve our communication systems?
Yes, that's an area where that is the only area where probably in all this thing I haven't worked. But I'll tell you, I showed one of the example, connectness, for example. I just talked about very brief. This is where, yeah. So ultimately, you need to first identify all possible types of connection and where the data are flowing from, whether the data are flowing within the industry only, it is going to outside the industry also. Because when you say industry 4.0, it is about network manufacturing. You will have to share some of the data with your supplier, some of the data with your customer, and within the industry also, and so on. So you need to first identify for a particular industry what is the data or the communication flow. First thing. Then how they are communicating, what kind of technologies they have used. And in that technology, you need to evaluate the risk. So there are various researchers, they work in the area of cyber attacks. So what they do is there are popular cyber attacks. I don't remember the name. Cobot related questions. There's some cyber attack is there. So you can simulate those cyber attacks. Ultimately, the cyber attacks are nothing but the program. So you can develop this program. You can hack the current system and show that this system is vulnerable to this kind of attack. First thing. Now, if you know that these are the possible attacks and this is how it affects, then you will have to design a kind of solution for that, or kind of antivirus solution for that. So again, a program, and that program needs to reside on either in the cloud or edge device or your PLC, or your local industrial PC in the local server, etc. So you need to decide what will be that program, where to put that program, and that program will again depend on a particular kind of threat. You know how the antivirus works. Every antivirus has capability to defend some of the cyber threats. So people know that these are the cyber threats. Corresponding to that threat, they design their antivirus. Similarly, you will have to design it and then put it into the right place in your network. That's how you can protect it. But it opens up a new area of defense in the cyber attack in manufacturing. I'm not the expert in this, but yeah.
Okay, thank you so much, sir. I think the answers given by you may clear that doubt. That's all. Over to you, Neha ma'am. Thank you, sir.
Thank you.
Thank you so much, sir. We came to end of this webinar. Rather, I must say this is the starting of sharing knowledge. We would like to organize so many such more interactive sessions with you, sir. Thank you so much. It was indeed a privilege to have Dr. B.K. Lad, our eminent speaker. I thank you, sir, for having spared your precious time for all of us for insightful lecture on smart manufacturing. Really, we need a smart thinking and dedication for applying this smart manufacturing. I thank you once again, sir. I would also like to extend my gratitude to Professor R.K. Saxena, Honorable Director, Dr. M.D. Dandekar, Professor and Head of Industrial and Production Engineering Department, all my senior professors, including Professor R.C. Gupta, Professor G.D. Thakar, Professor A. Dalpati, and all senior faculty. Without them, Without their guidance and support, we are not able to complete this webinar very successfully. Thank you to all. I also thank to my webinar team, Dr. K.K. Dhakar, Praveen Memroth, Anil Sharma, Sumit sir. Thank you all for your support. Last but not the least, all our beloved participants. Thank you for joining us. I hope everyone is benefited with this webinar. And we will looking forward to see you soon with more such interactive webinar. Thank you so much. And thank you, sir, once again.
Thank you for inviting me. Thank you, everyone.
Thank you, sir.
ओके
Yes, sir.
बढ़िया रहा. Thank you
Praveen,
everybody. Anil, Sumit, Neha, Krishnakant, everybody has done great job. Thank you very much, all of you.
थैंक यू सर.
तीन ही लोग दिख रहे हैं यार, बाकी लोग का है? सुमित, नेहा, कृष्णकांत, अनिल और प्रवीण का है.
प्रवीण सर शायद YouTube में बंद कर रहे होंगे, सेटिंग वहां पर YouTube में कर रहे थे इसलिए.
ठीक है, ओके, ग्रेट जॉब. चलो बढ़िया.